Let me welcome you to this lecture. We have been discussing the chemistry of hydrides of boron, and so far we have looked at the structure of some of these boron molecules or boron clusters. So now the shape or the cluster, the structure of these boron clusters can also be predicted by looking at the number of electrons that are essentially used for formation of this skeletal structure of these molecules, and this method for finding out the structure or predicting the structure of boron molecules or boron clusters by calculating the number of electrons used for formation of the skeleton was developed by Kenneth Wade initially. So this set of or this method or these rules for finding out the structure of boron molecules by calculating the number of skeletal electron are also sometimes referred to as Wade's rule. Also, David Mingos did some improvement on the rules that were initially proposed by Kenneth Wade, and that is why sometimes these set of rules are also known as Wade Mingos rule. Uh, Moreover, because this method for finding out the structure of boron molecules essentially involves calculating the number of skeletal electron pairs which forms the skeleton of the cluster in these boron molecules. That is why these set of rules are also known as skeletal electron pair counting method. So essentially we will learn during this lecture how we can find out the structure of boron molecules as well as substituted boron molecules along which other cluster compounds structures can also be found out by following this set of rules or by extension of this set of rules, and we will learn about how we can find out the structure of not only boron molecules but as well as substituted boranes like carboranes, as well as structure of metal clusters by using this skeletal electron pair counting method. Now this set of rule proposed by Kenneth Wade is essentially based on one principle, that is for formation of a polyhedral structure with n vertices, n plus 1 bonding MO molecular orbitals are required. And in these n plus 1 bonding molecular orbitals, essentially one will have n plus 1 electron pairs. So these n plus 1 electron pairs are essentially going to form the skeleton or the cluster in these cluster compounds. And now from here what we can do is that in order to find out the structure of a boron molecule or as well as a substituted boron molecule or say any other clusters, we will follow a certain method, and these steps in this method are essentially, first one will have to find out the total number of valence electrons in the system, that is count the total number of valence electrons from the formula. So now we will do it only for boranes, and later on we will extend these rules for substituted boranes as well as for other metallic clusters. So we will stick to only borane clusters during this lecture, or we will find out the structure of borane clusters by using this skeletal electron pair counting method, and we will extend these rules later on. So the next step, so that is we know that each boron atom, how do we count the number of total valence electron in the formula? Say if you have a boron cluster with formula say BnHm, we know for each boron atom has got 3 valence electron, so we will have 3n electrons, valence electrons from the boron centers, and each of these hydrogen atoms will have 1 electron, and so that is why total number of electrons in the system in a boron molecule with this formula BnHm is going to be 3n plus m. So that is how we can calculate the total number of valence electron in the boron molecule. And then next what we will do is that, because we are now focusing on finding out the number of electrons that are essentially used for formation of the skeleton of these clusters, so we'll have to ignore, or we'll have to deduct the electrons that are used for formation of 2 center 2 electron terminal BH bonds in these boron clusters. And that is why what we will do is that we will take the total number of valence electron in the formula and then deduct the number of electrons that are used for formation of 2 center 2 electron terminal BH bonds, because these bonds are not part of the skeleton in these boron clusters. So deduct 2 electrons for each BH group present. So because we know for each of these terminal BH unit essentially is formed by terminal BH bond is formed by 2 electrons, one from the boron, one from the hydrogen atom. So total we will have to deduct 2 electrons for each of these BH units from the total number of valence electrons for that particular formula present. Deduct 2 electrons for each BH group present from the total valence electron count. And this will give us the number of electrons that are left, or the number of electrons which are not used in 2 center 2 electron terminal BH bond formation. And these number of electrons, or these electrons are going to form the skeleton, or will be used for formation of all the linkage which essentially makes the skeleton of these boron clusters. And these electrons, or the number of electrons that we obtain after deducting the 2 electrons for each of these BH group present from the total valence electron count, we will call this number as the number of skeletal electrons. So this is essentially the number of skeletal electrons that we will get. And then in the third step, what we will do is that divide the number of skeletal electrons by 2. So that will give us the number of skeletal electron pairs. So because we divide it by 2, so that will give us the number of skeletal electron pairs. So in short, a capital SEP, we will abbreviate it for skeletal electron pair. Now we can predict the structure of a boron cluster, or structure of any cluster for that matter, from the number of skeletal electron pairs, because we know for formation of a polyhedral polyhedral structure with n vertices, n total n plus 1 skeletal electron pairs are required because there are total n plus 1 bonding molecular orbitals in such a system. So what we can do is that we can now find out the structure of the boron clusters because for boron molecules with n boron atoms and n plus 1 skeletal electron pair, if we have in the boron molecule or in the boron cluster, if we have n boron centers and if there are n plus 1 skeletal electron pair, we know we will have a cluster or a polyhedron which n vertices is going to be the structure, and because there are n boron atoms, these n boron atoms are going to occupy all the vertices of this n cornered polyhedral structure, and that is why we will end up with a closure structure. So what we will have is a closure structure with n vertices. So if we have, say for example, if we have now if we calculate the number of skeletal electron pairs for B6H6 negative, which is a closure boron, we know for this particular boron cluster, we will get, if we count the number of electrons now, what we will have is there are 6 BH unit, we know. So total number of valence electrons, let us count first. Total valence electron is given by 3 into 6. There are 6 boron centers. Then we have 6 hydrogen, so 6 into 1, as well as we have 2 negative charges. So that also we will add 2 electrons for both of these 2 negative charges. And the total number of valence electron that we get now, 18 over here, 6 plus 2, so 18 plus 6, 24, and this comes out to be 26. So 26 electrons are there total valence electrons. Now what we will do in the next step, we will deduct the number of 2 electrons for each of the BH units present. There are 6 BH units, so 6 BH, so that is equal to 2 into 6 equal to 12. So we will deduct these 12 electrons for 2 center 2 electron terminal BH bonds, and this will give us essentially 14 skeletal electrons we will get. And if we now divide these 14 skeletal electrons by 2, we will get 7 skeletal electron pairs. So what we have here is we obtained 7 skeletal electron pair, and we know now for 7 skeletal electron pairs we can have a polyhedron with 6 vertices is possible, or the structure is going to be based on octahedron because the n value here is going to be equal to 6, and since in case of B6H6 negative we have 6 boron centers, all of these 6 vertices are going to be occupied by boron centers, so there will be in the octahedral structure all the vertices are essentially going to be occupied by boron centers, and it is going to be a closed polyhedral structure, and the structure is going to be closure. We have a closure structure over here. So that is how we can find out the how by calculating the number of skeletal electrons or number of skeletal electron pair, we can predict the closure structure for a boron molecule. Now let us see the number of electron pairs or the number of skeletal electron pairs for a nidoboron. It is going to be for boron with for n boron centers, or let's write for borons with n boron atom and n plus 2 skeletal electron pair. will have nido structure. So let us take B5H10, for which we have drawn the structure in the last lecture. So if we calculate again the total number of valence electron here, 5 into 3 plus 10 into 1, so that is 15 plus 10 is 25 valence electrons. From here we have to deduct the 5 BH groups, we can terminal BH bonds. For each of the boron centers, we will assign one hydrogen atom as terminal BH hydrogen atom. So that is going to give us 5 into 2, that is 10 electrons. We have to deduct, so this gives us 15 skeletal electrons, and B5H9, the structure should have been, it is not B5H10, it is B5H9, so it is 9 into 1, and this is going to be equal to 24, because we ended up with an odd number over here, so and we cannot divide it by 2 for sure, and we will not have the correct skeletal electron pair value over here. So again 14 valence electron, which is 14 skeletal electron, and that is giving us 7 skeletal electron pair. So what we have seen is that for B5H9 as well, the total number of skeletal electron pair is equal to 7 skeletal electron pair, as well as for B6H62 negative also the total number of skeletal electron pair is 7. So both of these two structures, B6H62 negative as well as B5H9, this boron molecule, they are based on, for them, they are both based on, or in both of these two cases, because we have 7 skeletal electron pair, so n plus 1, that is for here also n is equal to 6, and in this case also the basic structure or the parent structure is essentially the octahedron or a polyhedron with 6 vertices. But here what is happening is that we do all the vertices, because we have only 5 boron centers which can occupy these vertices, and one of the vertices of this octahedral structure is going to be left empty, and that is why we have what we have here is a nido structure, or is a open nest-like structure, as one of the vertex of the octahedral structure here is left empty. So from here, by counting the number of electrons, what we have, if we take this as BnH n plus 4, from here we know it is the number of skeletal electron pair that we get over here, because n here is equal to 5, so it is, we have n plus 2 skeletal electron pairs are present in this structure, and that is why from here we also, by looking at the number of skeletal electron pair and then comparing with the number of boron centers that are present, we can tell that it is going to be a nido structure. As for n boron centers with n plus 2 skeletal electron pair, it is going to be nido structure. So let us proceed further and then calculate also the number of electrons, skeletal electron pair for a rational structure. So for borans, which n boron center boron atoms and n plus 3 skeletal electron pair is going to be a rational structure. So let us once again take the boron, a molecule that for which we have drawn this structure in the last lecture, that is B4H10, and calculate the number of electrons or skeletal electron pairs. Here we have 4 boron center, so 4 into 3 plus 6 into 1, so that will give us a total skeletal electron, so total valence electron. So this is 4 into 3, this is 12 plus 6, so 18 valence electrons are there. So from here again 4 BH we have to deduct. So 4 into 2 is going to be equal to 8 valence electron. So it is 10 valence electron, sorry, skeletal electrons. Skeletal electron, and this is essentially 5 skeletal electron pairs. Sorry, this is before H10, so that is why this is 10 and this is going to be equal to 22 and 22 minus 18 so minus 8 is 14 skeletal electron pair, and again we end up with 14 skeletal electron and 7 skeletal electron pair. So from here again what we see, that B4 H10 like B6 H6 2 negative and B5 H9 also has 7 skeletal electron pair, and again for formation of the polyhedron that is going to be formed for a 7 skeletal electron pair is going to be an octahedron, because again n plus 1 electron pairs are, if we take it as n plus 1 electron pair, then n here is going to be equal to 6. So the polyhedron will have 6 vertices, and not all of these 6 vertices of the polyhedron are going to be occupied by boron atoms, because we have only 4 boron centers in this boron molecule. So 2 of the vertices are going to be left empty, and that is why we will have an arrangement structure from here. Again what we see, and then on the n, if we take this as Bn and H n plus 6 here, so for this we see that we have, for n boron centers we have n plus 3 because n here is equal to 4, so n plus 3 skeletal electron pairs are present in this boron molecule. And from here again what we can say is that from this rule we can say that it has a irrational structure. So this is how we can calculate the number of skeletal electron pairs in a boron molecule, and then compare it with the number of boron centers in the boron cluster, and then from there whether it has n plus 1 skeletal electron pair or n plus 2 or n plus 3 skeletal electron pair, we can tell whether it is a closure structure, nido structure, or it is an irrational structure. At the same moment what we can tell is that we can predict the structure, because we know the structure of the parent polyhedron or the polyhedron structures of the polyhedron on which the structure is essentially based, because even for before H10 we could find out that the structure has to be based on an octahedron, because again for formation of an polyhedron which n vertices there must be n plus 1 total skeletal electron pairs, and from here itself we can say that it is going to be based on an octahedron. So this essentially brings us to the end of this lecture, and we should do calculation or do the skeletal pair counting for different boron molecules, and then find out the structure of these boron centers as a practice for this particular exercise. So thank you very much for being with me during this lecture.